Okay guys, let's continue with the second order systems. So in our last class we learned that second order systems, they are systems which obey the equation b divided by s squared plus as plus b, where we said that you have different types of these kind of systems, right? So firstly you have your overdamped systems, then you have your underdamped systems, undamped systems, and critically damped systems. So with an overdamped system, you see that the poles are located on the real axis. So both poles are on the real axis. While with an underdamped system, you'll see that they are real plus imaginary. So they have both real and imaginary parts, right? And when it comes to undamped systems, you see that they are marginally stable systems. They only have an imaginary part on them. And critically damped systems, their roots are real and repeated. So this is where we started off with our discussions. Continuing on, you'll see that we looked at certain aspects of these second order systems, namely their natural frequency and the damping ratio. So let's just recap on that as well as we go over here. So you'll see that the natural frequency omega n, as it is called, if you have a general system which is b divided by s squared plus as plus b, then omega n, which is the natural frequency of oscillation, is defined as the square root of b in radians per second. Then the damping ratio, it is defined by the Greek letter tau is equal to a divided by 2 omega n. And we did a few examples here, like for example this question that we have, where we're given the transfer function of a system, right, and we are asked to find out what is the natural frequency as well as the omega n, which is the tau. So finding omega n first. Omega n is equal to root of b. In this case it will be root of 36, which is equal to 6 radians per second. And then over here you will see that tau is equal to a divided by 2 into omega n. So it will be a divided by 2 omega n, which will be 4.2 divided by 2 multiplied by 6. So if you calculate that value, what do we get? So it's 4,2 divided by 12 essentially, which is 0,35. So the answer is 0,35 that you get, right? So now from here we then went on to describing these second order systems in terms of their value of natural frequency, right? So if you now make a comparison there, you will see that, let's just bring this down a bit, right? Let's paste, right? So based on the damping ratio, if the damping ratio is equal to 0, then you can see that this system will have poles on the imaginary axis, right? Now if the and it will be undamped, obviously. Now if the system has got a damping ratio between 0 and 1, then the system is underdamped. If the damping ratio is equal to 1, then it is critically damped. And we said that if the damping ratio is greater than 1, the system is overdamped. So this is in addition to what we discussed previously, where we just talked about the location of the roots. Okay, right. So now, going further into this topic, we will see that we have a few questions here that you can try. Example 4.4. And once you're done with the example 4.4, we go into detail about underdamped second order systems. So we are interested in focusing only on the underdamped second order systems. This is because they exhibit certain properties which will be useful for our system design later on, right? So these are some of the terminologies that we need to use. So for example, if you have a look here, we will take this section here, right? So we've already talked about the natural frequency. That's something that we have spoken about, natural frequency. We also talked about the damping ratio. On top of that, we are adding rise time, peak time, percentage overshoot, and settling time. So rise time, if we have a look here, TR is the time it takes for the system to reach 98% of its final value, right? And then peak time is the time it takes for the system to reach Cmax, that is the maximum amplitude. And settling time is the time that it takes for the system to settle into a final value, which is around 2% of the final value. Rise time, 90% of the final value. I think I mentioned it as 98, but it's 90% of the final value, that is rise time. So we need formulas for calculating each one of these, and that's what we're going to look at next. So we start with the evaluation of TP. You can see that this is the way you calculate TP. TP is equal to pi divided by omega n into root of 1 minus 2 squared. And then if we go on to the percentage overshoot, so it is measured as a percentage, so it will be e raised to minus 2 into pi divided by root of 1 minus 2 squared into 100. So into 100 is where the percentage comes in, and it is expressed as a percentage. While peak time, the one that we discussed previously, is measured in seconds. Then if you go into settling time, the formula is 4 divided by 2 into omega n. And rise time is defined as normalized rise time. So rise time, the formula is slightly different. So this is the rise time. So TR is equal to normalized rise time divided by omega n, right? So if you have a look here, there is a formula for calculating the normalized rise time. So here's the normalized rise time. So if your 2 is 0.1, then your normalized rise time is 1.104. So in this case, let's do this example here where you have the transfer function 100 divided by s squared plus 15s plus 100. So we need to solve and find out what is the different values there. So let's try and do that. So the question is 100 100 divided by s squared plus 15s plus 100. Right, so omega n, which is the first calculation, is going to be root of 100, which is equal to 10 radians per second. Then the next one is tau, which is a divided by 2 omega n, which is 15 divided by 2 into 10. How much is that equal to? 15, that's 0.5, isn't it? No, that should be 0.75. 0.75. Then we have peak time Tp, which is equal to pi divided by, what was the formula that we had? Pi divided by omega n into root of 1 minus 2 squared. So omega n into root of 1 minus 2 squared. Settling time Ts is equal to 4 divided by 2 into omega n, and the percentage overshoot is equal to e raised to minus 2 into pi divided by root of 1 minus 2 squared, the whole into 100. Then the last term that we need to determine is the rise time, Tr, which is equal to the normalized rise time divided by omega n. So in this case, our tau is equal to 0.75. So the normalized rise time is given in the question. That will always be the case, and you'll see that the normalized rise time is 2,3 seconds. So there it is. It's given as 2,3 seconds, right? So the formula that we're going to be using here is 2.3 divided by omega n, which we calculated as 10 radians per second, divided by 10, which is equal to 0.23 seconds. So this is a pretty important question which might be a possibility for the first test, which is the calculation of these values. Remember, the class test is going to be on what we covered in the first module and all up to this point that we have worked out now. So as far as your textbook is concerned, it will be, let's have a look here, the introduction chapter, the modeling in the frequency domain, and in the time response we're just going to, we're gonna stop by this point where we do the calculations. Yeah, like this question is an ideal example that we can focus on. Okay, right, so we'll continue with class right after